Hello, folks. Thank you so much for coming on this last day of the conference. Super pumped to talk about STPA. So truly welcome to this talk about illuminating the unknown unknowns. My name is Theo. I'm a site reliability engineer on Google Maps, and I'm here with Ruben and Garrett. Ruben?
Hi, I'm Ruben. Can you hear me? Yeah, I'm Ruben. I'm an SRE working in Google Maps. I'm based in New York.
I'm Garrett. I'm a technical writer. I work on SRE documentation at Google.
Awesome. Okay, and with that, let's dive right into it. So this talk is going to be interactive, okay? So we want your help with this talk. Now, when you see this gray box with a question mark in it, please open up Slack and respond to the pinned thread. I've added a comment there where there's like a speaking head emoji. So please use that for answers to the questions that we ask you. And feel free to join that specific Slack channel. Okay, hopefully it won't be super chaotic. Sup, I'm reading your threads right now. Okay, so let's get right into it. So let me clarify what we hope that you take away from this. Our goals are that after this talk, you can describe what STPA is, how it works at a high level, and you can give some examples of how it can even be applied to systems, both human and software, and it can even anticipate incidents. Great. So let's open up with a story about how I was recently paged for a system that I'm on call for called the road disruption system. Now, the goal of this system is to process road disruptions from third-party providers and serve those road disruptions to end users. So when a third party tells us that a road is closed, like here is 25th Street, we should ensure that that road is closed on Google Maps. Likewise, for when a road is reopened, so here we can see it was deleted from the third-party database, it should also be deleted from Google Maps. So this is a super straightforward responsibility, synchronize road closures between two different systems. Great, it's the middle of the morning, and I have been manually paged because a bunch of our users are being routed through a street that is closed due to a parade. This should have never happened. I look at our dashboards and I see no SLOs were violated. All of our services show green. And every service worked as expected. How could this happen? Now, after extensive investigation, we discovered that in spite of everything working as designed, it was the interactions between the services that were misconfigured. Key services made incorrect assumptions about how other parts of the system behaved. Now, in order to fix this, the developers and I now need to spend 2 months rejigging and redesigning the system. How could this have happened? How is it possible that we had an incident that was based on a system design flaw? Well, what I just described is a pretty common story in software development and in general, the life cycle of a product. So this should be pretty familiar. Of course, the life of a product goes like this. You write your design docs, you get it reviewed and you get it approved. Then you build your product and launch it with a gradual rollout, making sure everything works. You continue by monitoring it to make sure that the product meets the SLOs you've defined. And maybe you make more improvements and new features until at one point, boom, incident. You send a bunch of people down a parade route that's supposed to be closed on Google Maps. So of course you triage, you mitigate, you resolve, and you follow up with a postmortem. After understanding the postmortem and figuring out what happened, you actually realize that there was a design issue. So of course you apply the fixes, you redesign part of the system, you create new rules or guidance to prevent other teams from hitting this exact same problem, and the cycle continues until you have the next incident. But what if I told you there existed a process where you could methodically anticipate the ways your system could break at the design stage when your system existed on paper only? And this process could help you come up with a thorough list of all of the ways your system might have an incident, along with the causal factors that would lead to those incidents. And with that list, you could essentially fix those design issues before they blow up as an incident, effectively preventing it from ever happening. Well, let's look at the cost implications of that process. So, the traditional life cycle, super costly. We don't really realize this, but it actually is super costly. A study at the Software Engineering Institute at Carnegie Mellon found that most failures are introduced at the design stage of a product. However, they're found in the testing and production stages where the cost to fix those defects is way higher. Now these boxes, they don't have any percentages on them, but the source down below, when you get the slides later, that has the actual numbers there. Now, what I was describing about this mysterious process, what it does is it moves the detection of failure modes to the earlier stages of the product, where it is way less costly to fix, because it's much easier to change a few sentences in a design doc than it is to rework something that's in production. This is super intuitive, right? So you might be wondering, what is this process, and does it really work? Are you like a snake oil salesperson? And well, I'll answer the first question. So spoiler alert, the process is STPA, and hopefully you expected that to be the response based off of our talk title. Now, STPA stands for Systems Theoretic Process Analysis. Now, even though it's an acronym, I will be using STPA as a noun throughout this talk, okay? So just think of STPA as this entity. Great. So our claim is that STPA can anticipate incidents. Now, before we show you what STPA is or how it works, let's do a warm-up activity together so that we can feel for what it is like to anticipate what might go wrong with a system without the use of any specific method. Okay, so let's put on our thinking caps. Let's brainstorm together, okay, with a system that we're all familiar with, the incident response system. So quick raise of hands, how many of you have ever been on call for a system? Amazing, so you're all experts, right, in the system of incident response. Perfect. Okay, so let me present you with a hypothetical scenario that has probably not been hypothetical for any of you. I'm sure that most of you have gone through this scenario before. So your production service starts returning errors, and then you kick off the incident response. And there exists some correlation between a rollout that just started and an increase in server errors. Now, your on-caller does not roll back the service to a previous version. Okay, that's the key thing. And as a result, your customers experience a prolonged incident. Now, this is your time to answer the question. Why would the production service not be rolled back? Now, I want you to think about this question and write down some ideas in Slack. So we see a correlation between errors and the rollout starting, and in spite of that, the on-caller does not roll back the service. And because of that, you have a prolonged incident. I'm seeing backwards incompatibility. Yep, schema change, RIP, totally. Percentage of affected traffic was too low, 100%. The on-caller was not confident. On-call isn't aware of, yep, totally. I mean, sure, yeah, important clients, they just want that now, and 10% of the users don't matter. Compliance fix, business impact, confusion by the numbers on the y-axis. Yep, yeah, I mean, 800% error rates. Thank you, Gemini, for that. Okay, you guys are going crazy. Okay, yeah, not proven that the rollout was the root cause. So confusion for sure. No rollback already exists. Yeah, dependencies for sure. Okay, this is awesome. Thank you guys so much. Okay, so these are all great reasons. Now, one other reason I think we might have stated here, an on-caller might have misread the dashboard that shows service errors. I mean, they might have seen 800% and been like, what the heck? And talked to the person who designed the dashboard instead. So these are all great examples. Now, what we're going to do today is show you how we would have applied STPA to the situation, and then we'll come back to this exact question to figure out whether or not we can generate new insights using this methodology. As we're going to see later today, STPA provides a structured method to do what we just did with our warm-up activity. You see, the thing is, all of these questions here, or all of these answers rather, heavily depended on our intuition and our lived experience. So it's kind of like an artisanal craft. STPA provides the structure that allows us to methodically find all of those scenarios. And it typically results in deeper insights and enables us to find more of these scenarios than we would have done otherwise. Okay, Now, raise of hands, who has heard of STPA before this talk? Oh my God, that's amazing. I gave a talk on this last April at SREcon, and there were fewer hands than this, so I'm excited about that. Okay, so let's go through what STPA is. Now, STPA is a paper and pencil method that involves modeling the behavior of a system and then analyzing how that behavior can be unsafe. The output of STPA is a comprehensive list of all of the ways that we can have a loss. Now, STPA uses the word loss to mean an unacceptable outcome for all of our stakeholders. So our stakeholders could be vice presidents, our customers, our engineering organization, okay? So these are unacceptable outcomes, and this might be the impact of an incident. So an incident itself might not be a loss, but the outcome of that incident might result in a loss. Now, STPA has been in use for many years by safety engineers in other industries, like aerospace, nuclear, medical, and Google applied it for the first time in 2020. And since then, we've run several analyses within Google. We're not the first software engineering company to apply STPA, but we really are pioneering the application of it to software design. And I really want to highlight that point about software design. As I mentioned earlier, you can use this methodology to find design flaws when all you have is a design document, okay? How many times can you predict methodically all of the ways your system's going to break when you don't even have the system at all? So the question now is, I'm sure you guys are thinking this, does this actually work? And our answer is yes, it does work, of course. Otherwise, we wouldn't be giving this talk. Now, Google Maps was one of the earliest adopters of STPA, and so we're going to demonstrate some examples that come from Google Maps. And we've been able to find and fix the issues that before they caused those incidents, both on designs on paper and on mature systems within Google Maps. Now, even when STPA finds an incident scenario that has already happened, it often reveals additional factors that might have only been partially addressed in the previous postmortem. And as a result, we've done some good work within Google, and people have started coming to us and started asking us for more STPAs. And there are a few of us facilitators. We don't have too much bandwidth to do it, and so we have a huge backlog now with STPA analyses that we want to run. Okay, now the real proof that STPA works. So we actually ran STPA on this road disruption system, and this particular incident that I'm showing here actually never happened. And this is because we identified the design flaws that would have led to this incident and fixed them before our system even launched. Great. So we're going to see exactly how we did that later in this talk. So why did we name this talk Illuminate the Unknown Unknowns? Well, as SREs, sometimes we know that there are areas in our system that are risky, but we don't know the specific risks. And those are the known unknowns, right? And we can allocate bandwidth to help find those risks in those areas. But what really keeps us up at night is the hidden risks that no one has considered, that no one is even looking for, really. And those are the unknown unknowns. However, now we have a method for illuminating that space, okay? STPA is kind of like having a flashlight and being told where to point that flashlight in order to illuminate this space of unknown unknowns so that you can start reducing your risk exposure. Wow, that was a pretty extensive sales pitch on STPA. So I'm going to take a quick breather, and then I'll present to you with the agenda for the rest of the talk. So first, we're going to walk you through the 4 steps of STPA. Then, like we did in our warm-up activity, we're going to use our new understanding of STPA to analyze that system of rolling back, of an incident responder rolling back a binary. And we're going to try to find flaws in the system that might worsen an incident in progress. Then, because this is a long talk, we're going to take approximately a 5-minute break halfway through. And then finally, we're going to show you how we ran STPA on the road disruption system. Now, quick disclaimer. STPA cannot be taught in only 90 minutes. What we hope you learn from this talk is how you can describe, So what we hope you can learn really is the ability to describe how systems theory can help you anticipate your incidents before they happen. So with that, I'm going to hand it over to Ruben to start describing the STPA methodology. Great. Thank you.
We like to say that STPA is methodical and teachable. And as Theo just mentioned, STPA has 4 official steps. And let's go through those steps together. So we'll start with a quick overview of STPA, and then we'll dive into the specifics of each of those steps. Step 1 is about scoping the analysis. We define the losses that, as Theo mentions, are the things that the stakeholders in the system want to avoid. Then we define the unsafe system states that could lead to those losses. In step 2, we model our system. We use control feedback loops, which are a very different model from standard data flow diagrams that we use often. And we are modeling here behavior and control happening in our system, not just data flowing through the components of the system. And in step 3, we will list the control actions that could put the system into one of those unsafe states that we've identified in step 1. And lastly, step 4 is where we build the loss scenarios. These explain how these unsafe control actions that we defined in the previous step could actually happen. And the great thing is that we can now trace all of these scenarios straight back to where the losses that they can lead to. And this is a key for later prioritization. Finally, we get to an extra step, step 5, mitigations. STPA is not prescriptive about what to do with all the things that we discover, all those scenarios. Now we have to engineer the solutions to address those scenarios. And the questions are of the form like, which scenarios do we prioritize for mitigations? How do we implement those mitigations? Those are purely engineering questions. Now let's walk through the steps of STPA using a familiar scenario, the basic incident response protocol. You might recall that Theo asked you earlier, why might the bad version of a production service not be rolled back? You all have great answers. And now we are going to take that exact question and we'll apply STPA to find out all the ways in which that can happen. And once we've identified the hazards, we'll then find concrete ways to reduce or eliminate those unsafe actions surrounding this incident response protocol. So, step 1, scoping our analysis. The first thing we do in STPA is to define the losses. So, these are the unacceptable outcomes for our stakeholders in the system. And at Google, we found that the losses tend to be of similar nature for most of our internal software systems. But in general, common losses that you can find in an STPA may include loss of revenue, loss of brand trust, loss of legal compliance, and sometimes, depending on the application, depending on the system, injury or loss of life. And here is a key rule of thumb to defining losses. Your losses should not reference low-level system details or specific causes that lead to them, like networking errors and others. But we are not done with step 1 yet. The other thing to do in step 1 is to define the hazards. STPA is a hazard analysis technique. That's a bit of a mouthful, but all it means is that we systematically look for all the things that could cause any of the losses that we just identified. Specifically, a hazard is defined as a system state that will lead to a loss under worst-case environmental conditions. And throughout the analysis, we label these hazards and reference them throughout the steps. For our incident response example, a simple hazard might be our production service is returning errors. Now, question for the audience. I have a good question. I just said that a hazard leads to a loss only under worst-case environmental conditions. Can you think of a reason why this particular hazard, production services returning errors, might not lead to a loss? Feel free to type your answers on the Slack channel. error rate, expanding error budget at acceptable rate, mitigating or compensating conditions, retries mitigate the errors are not visible to users or other systems, product is not yet launched. Yeah, all those great answers. So exactly, so for example, it's possible that our service is returning errors, but this happens late at night when there is very little demand. The impact to our users is so small that we have no loss of revenue or brand trust. But if the incident occurs during peak demand, the loss happens. So defining these hazards is critical because they guide our reasoning in the later steps of the method. And if we can determine all the ways in which the system can enter this hazard state, we get a complete picture of the overall safety of our system. And then we can redesign the system to prevent those unsafe actions. And that's the engineering part. Finally, we often say that hazards give you time. So why is that? Remember the low demand scenario? So the hazard state, production services returning errors, existed, but the loss did not occur. So that hazard state might exist for hours or even days before the worst case conditions come up. And if we can't prevent the hazard state entirely, we can at least make sure that we detect the hazard and that we have the means in place, the means in the system in place to move the system back to a safe operation state. Now let's move to step 2, which is about modeling our system. So we do this by drawing a control structure, which is composed of control feedback loops. Quick poll for the audience. Raise your hand if you have heard of control theory. Wow, quite a lot of people. Nice. For those of you who have heard of that or used that, anyone has used control feedback loops to reason about a software system before? A few, still quite a few hands. Nice, that is great. Now I'm going to quickly build a basic control feedback loop on the slide and explain the parts as we go. So we start by identifying the control processes at the bottom. These are the parts of our system whose behavior we have to constrain. Next, we identify the controllers above those. Controllers can be hardware, they can be software, or even humans. In fact, in any non-trivial control structure, you will always have human controllers involved. And these controllers decide on what actions to take. I mentioned earlier that the STPA models component behavior happening in the system. Well, what is behavior if not a series of decisions? STPA calls these decisions control actions. And here's the very important part. Controllers don't make decisions out of the blue in a vacuum. They base their decisions on feedback coming from other parts of the system, often directly from the control process that they are controlling. And with this simple control structure built, we now have the framework to reason about how our controllers might make decisions that result in a system hazard. And we'll do that in the next part of the analysis, which is step 3. Again, remember our motivation here. We are modeling all of these because hazard states can lead to losses. And we are trying to anticipate and prevent the system entering those hazard states. Now, to make sense of all this theory, let's model our rollback example as a basic control feedback loop. We could add more controllers to expand the scope of the analysis, but for today, we'll keep it to this single loop. And we are going to analyze the key decision to roll back or to not to roll back the production service to a previous version. And at the top of the loop, we have, indicating higher authority, we have the controller. In this case, an SRE, it could be you. And all controllers have a control algorithm, all right? For a human, we call this decision-making process. And this process determines exactly what control actions the controller takes to constrain the behavior of the control process. For this example, our key control action is roll back to a previous version. of production. Remember that a controller can have multiple control actions, but we are focusing only on this particular one. The control process at the bottom is the production service, and we want the SRE at the top to constrain its behavior to keep it safe. And we know what safe means for us now because we defined our hazards and losses back in step 1. For instance, SRE must prevent the production service from entering the hazard state where it is serving errors. Or like in this case, the SRE must detect when the system enters that hazard state, which is when the production service starts to return errors, so that they can decide to roll the service back to a good version. The controller receives feedback from that control process. In our example, that is the response errors, the rollout timeline, and possibly customer escalations that arrive to the SRE team. Again, there can be multiple pieces of feedback flowing into a controller. All controllers also maintain an internal model of the control process state. For humans, we call this a mental model. For a software or automation, it's a process model. And critically, the controller's belief about the state of production might be wrong. And this can happen due to missing feedback, bad data, or simple and incorrect interpretation of what they are seeing. And based on that mental model and their decision-making process, the controller decides whether to take another action, and the cycle continues as a dynamic process. And we've seen that modeling systems in this way has a significant effect on how our engineers at Google and SREs think. For one thing, product developers tend to be excellent at designing the control path. However, feedback paths are rarely formally designed. And we often uncover incorrect assumptions about the feedback coming from another system. Other times we discover that critical feedback is completely missing in the system. And once we have our control structure, we start to actively looking for system issues. And that starts with figuring out exactly how those control actions might put the system into a hazard state. Now, I'm going to foreshadow the next steps of STPA a little bit here. Let's see how this model of a controller can help us reason about what goes into the decision to roll back or not roll back the production service. And we'll examine the mental model first. So one question for you all, feel free to type your answers in the Slack channel. As an SRE, what do you need to know about the service in order to safely decide whether to roll the service back to a previous version of production? What's inside that mental model? Do I lose data? Error rates? Potential fixed bugs reverted? Yeah, fixing other issues. Rollback path exists, speed of rollbacks, great. We're all great analysts. So, great discussion. So we had two examples on this slide of important factors for an SRE's mental model. One might be whether the production service is returning errors. And another might be that the SRE's belief on whether or not the issue correlates to a recent rollout. We simplified the mental model here. There might be other mental model variables, but for the sake of discussion, let's move forward. So now let's examine the SRE's decision-making process. So, question for the audience. How do you decide whether to roll back the production service? We are looking for something like pseudocode here, very simple, like an if-then statement inside the decision-making. Feel free to add the question, the answers in the Slack channel. If simple feature flag change, then rollback. If errors come from new version only, then rollback. If stateless, then rollback, correct. If previous version worked and current one does not, then rollback. Good. All those are great. So our decision might be that if service errors correlate to a recent rollout, then we roll back. Another decision might be that if the incident is big enough, for example, the rate of errors rate is large, like 800%, then we immediately roll back, even if we have a lower confidence level that the errors correlate to a recent rollout. We often find that when we run STPA and ask people how they form their beliefs about the state of the system, the assumptions they typically make and the decision-making they follow, we are the first ones to ever ask these questions in such detail during the analysis. And this frequently leads to interesting discoveries about assumptions and how decisions are made. Again, in talking about the SREs model, mental model, and decision-making process, I am foreshadowing the next two steps of STPA. And now I'm gonna turn it over to Garrett so he can walk you through these other steps in more detail.
All right, thank you, Ruben. So on to step 3. So we've scoped our analysis, we've defined losses and hazards, and we've modeled the system. In the next 2 steps, we're going to use this model to reason about all the ways that unsafe system behavior, both from humans and from complex software interactions, might lead to losses. So in step 3 of STPA, we list out all the unsafe control actions, or I'm just going to use the abbreviation UCAs. So a UCA is a control action that, in a particular context, will lead to a hazard. And as we'll discuss, that context or the circumstances surrounding the control action is really key to whether that control action is going to be safe or unsafe. Now, my favorite sequence of slides. How do we determine whether a control action is safe or unsafe? So for example, I have a butter knife here. What about the action use butter knife? Is that action safe or unsafe? You can give me your response in Slack here. Okay, the first answer is it depends, okay? All right. Some people have seen the slide before, yes? Depends on what you're using it for. Safe always, Okay, so I think people have the point here. Context, context, context. So, use butter knife to spread butter on toast. That seems pretty safe. Use butter knife in electrical outlet is definitely not safe. And my first career was in electrical engineering, and I still enjoy restoring vintage electronics. I've been shocked several times. I can definitely confirm that knives and electricity do not mix. So by itself, a control action such as roll back to previous version is neither safe nor unsafe. You need to know the context. Context is key. So let's add some context and list out some UCAs, unsafe control actions, for our SRE who is deciding whether to roll back production to a previous version. One UCA is that it's unsafe for the SRE to roll back to the previous version when the service is not returning errors. I mean, that rollback is unnecessary, it's unsafe. You might be taking away features or even reverting a critical fix and then putting the system in that hazard state, as Ruben was describing earlier. What might be some other contexts where it's unsafe to roll back to a previous version of production? Go ahead and put your answers in Slack. Okay, security issues, if there's a security issue with rolling back. Dependencies, yes, that's come up. Data schemas. If the data schema has changed irreversibly. Release had a one-way database migration. Maybe a scaling issue with a peak hours rollback. If you don't have a playbook, I like that one. I'm a technical writer. I can relate to that. Data loss, the rollout system is broken, the rollout mechanism wasn't tested or was tested a long time ago. Excellent, all great answers about context. So here's two that we came up with. Simply invert the thing, it's unsafe to roll back to the previous version if the previous version has a production issue. And somebody called it. Our example was it's unsafe to roll back if the previous version is no longer compatible with production. For example, if there's been a database schema change. Great. And in one of my previous careers, I was a high school physics teacher. I very much appreciate audience participation, so please keep it coming. There's nothing more boring than somebody just talking for hours. All right, you can also have a UCA where the controller doesn't take a control action. So here's our example UCA from the previous slide. SRE rolls back to previous version when the production version is not returning errors. Looking at this UCA, is there a similar UCA where the SRE does not roll back? So it would start like SRE does not roll back to previous version when blank. And go ahead and type your IDs in the Slack. When is it unsafe to not roll back? Okay, we got a few answers coming in. New version is actively damaging stored data. System design is not clear and the blast radius. When the new version is genuinely broken and the old version is safe. These all might be reasons to roll back, though, I'm thinking. What about not rolling back? When is not rolling back unsafe? Or you're saying if you roll back, then you will get data corruption. I think that's what it is, yeah. Got it. Rollback is mitigating a high impact incident, yes. Problems with a different component, okay. Great. All right, so again, we just did a really simple one, an inversion. It's unsafe to not roll back to the previous version when the production service is returning errors. And you know that that's correlated to the rollback that just happened. All right, so our theme for this talk is that STPA guides you on where to look, where to shine your flashlight. Unsafe control actions is an example of this. Mathematically, and you'll see this if you look up the MIT information, there's 4 different ways in which rolling back can be unsafe. So sometimes it's unsafe to actually roll back. Sometimes it's unsafe when you don't roll back. It could also be unsafe to roll back at the wrong time, so maybe too early, too late, or out of order in a sequence that includes some other actions. And if we consider that the rollback action itself has some duration, it could be unsafe if you stop the rollback too soon or if you allow it to proceed for too long. So for example, just as you might have incremental rollouts, so you can see the effect of a new version on production, you might also have incremental rollbacks. So if you initiate the rollback and you immediately start seeing a lot of new errors, it's unsafe to let that rollback continue, potentially affecting more and more users. So by brainstorming context for all 4 of those cases, we know we've shown our flashlight, our STPA flashlight, on all the possible ways that this action or lack of action, or maybe even the timing of the action, can be unsafe. If we only think of ways for that first case where performing the rollback is unsafe, then we've left 3/4 of the cases in the dark, essentially. So now that we've illuminated the 4 different kinds of UCAs, let's see some examples of each. We've talked about UCAs where you take an action. It's unsafe to roll back when the current production service isn't returning errors. We've talked about UCAs where you don't take an action. It's unsafe if you don't roll back when the current production service is returning errors. Does anybody want to take a guess at a UCA where the SRE rolls back too late? Maybe type your answer here. Okay, so you got lost trying to root cause it, okay. Roll back too late when the VP has already been paged. I like that one. Roll back too late after you start getting a lot of customer calls. Okay, these are all good context. Yep. Company is out of business. That would be far too late, I think. Yes. Maybe you took too long to identify the correct binary to roll back. You've already had some data changes or some losses of data that have happened. Great, excellent, thank you. Okay, here's our example. Maybe it would be unsafe to roll back too late after the errors have started impacting users. Maybe another one. As I mentioned previously, it's unsafe to continue the rollback for too long. Actually, this is one of the next kind, so with duration. It might be unsafe to continue the rollback for too long when the rollback itself is resulting in new errors. So remember, we've done all this for a single control action, which is the SRE rolling back to a previous version of production, trying to decide whether to do that or not to do that. In a larger and more exhaustive analysis, we would have multiple control actions and possibly multiple unsafe control actions for each of them, all of them with different contexts that make that action unsafe and different types as we've listed on the screen here. The good thing, and something that we do a lot at Google, is that you can tailor your analysis to your available bandwidth. You can decide which areas of the controller structure and which UCAs you want to prioritize. So you can sort of decide based on the time that you have available where you want to focus your efforts in STPA. Okay, we're at step 4 now. This is where we're going to use what we've done in the previous steps to start anticipating possible incidents that might occur in our system. And again, STPA calls those loss scenarios. So we have our list of unsafe control actions. With that list in hand, we can now start going through them one by one and reason about why that controller would issue that unsafe control action, or in other words, why part of the system would behave in an unsafe manner. We know that UCAs lead to hazard states, and hazard states are going to lead to a loss under worst case conditions. So at the end of this step, we're going to have really a comprehensive list of scenarios, basically how unsafe behavior in our system can lead to hazards and losses. We're going to use our model of the system, again, that control feedback loop, to guide this reasoning. So we're going to pick a UCA, look at its control loop, and then ask the system experts a series of questions based on the different parts of the control loop. So unsafe behavior can really happen at any part in this loop here. That includes the decision-making of the controller, the feedback, the control path, and also even the control process itself. So something about the rollback in the production service. Okay, here we see our stick figure pointing the flashlight, showing that once again STPA is going to guide us on where to look. I've drawn a line splitting this control loop into 2 parts, and so far we've mostly been talking about controller issues. So in this case, how does the SRE decide whether to roll back? What is the SRE's mental model of production health? Is it accurate? You could also have issues with feedback to the SRE. Now, no slack here, just shout it out. I think it's a small enough room. What is the feedback that the SRE is using to determine whether to roll back to a previous version? Monitoring dashboards, yes, exactly.
Timestamp of the rollout?
Timestamp of the rollout, okay, I didn't catch that one. Alerting, yes, okay, excellent. This is a teacher's favorite moment when people have been paying attention, and getting great answers, yes, excellent. Okay, so if there's something wrong with this feedback, then the SRE is likely going to have the wrong mental model about production health. And that makes it likely that they're going to take an unsafe action. So again, STPA is guiding us to cover the entire control loop when we're coming up with scenarios that could lead to an incident. Now in the upper part of the diagram, we have controller and feedback issues. But at this point, we've only brainstormed half of the possible scenario space. On the lower part of the diagram, we also have control path and control process issues. Those can get really interesting. Ruben's going to show you some of those in a bit. First, let's take a look at controller and feedback scenarios. So I'm going to show you STPA's method for building loss scenarios, and this is a really powerful aspect of STPA. Again, this method is going to involve asking your system experts a series of guided questions to make sure that you shine your light on all the areas of the control structure where there could be issues. So let's revisit this rollback example and consider that first category, which is going to be controller and feedback issues. So again, we start by picking a UCA. SRE does not roll back to a previous version when we're serving errors. And in our diagram, we might have multiple types of feedback coming to our controller, but in order to build our question, we're going to pick one feedback. And for this example, we'll use the feedback that's present in the context, which is response errors. Now, there's two possibilities here. Either that feedback is safe, or that feedback is unsafe. Now, you might be wondering, why didn't I say correct, incorrect? Well, there's a reason for that. Safe feedback means that the correct feedback exists somewhere in the system. This is the case that we've been discussing in our rollback examples and the initial activity. And in a minute, I'm going to tell you why I'm using the terms safe and unsafe here. So first, I'm going to show you how STPA guides us to build the actual questions for the system experts. So again, this is just putting this out in text. We pick a UCA, pick a piece of feedback, do this twice, once for the case where feedback is safe, once for it's unsafe. And then finally, we ask our question. For the case where feedback is safe, the question would look like this. Why would the production service not be rolled back in spite of feedback existing that shows service errors? Now, this should look familiar. This is the same question that we asked in the initial warm-up. Only here, we're explicitly specifying that feedback exists showing server errors. And of course, we did this on purpose so we can get a better comparison here. Now, maybe we have a different perspective after talking about how STPA models the system and what can go wrong in that control feedback loop. So let's review this and see if we have any additional insights here. So again, looking at the control structure to get a picture of what we're doing, if the feedback is safe, but the controller does something unsafe, and no slack here, just shout it out, where's the problem?
Decision making.
Okay, decision making.
It could be the feedback, could be the whole decision making side.
Could be the feedback, decision making side. Okay, feedback going into safe, the SRE is getting the right feedback, but the SRE does something unsafe. Where's the issue lie?
They don't understand the feedback in their mental model.
Maybe the SRE doesn't understand the feedback. I think
The actuation of the decision, not just the decision made too.
actuation of the decision, yeah. So I also think that this is a crowd that believes very strongly in blameless culture, so nobody wants to say it's the SRE. But yes, like something is going on there, and it's not necessarily blame here, it's the system, right? You get safe feedback, unsafe action. There could be many reasons for that. Maybe there's a learned process that the SRE is using. Maybe it's something about training. I work in training a lot. You know, we're gonna try to uncover that, right? Great. All right, so we wanna understand, could there be flawed decision making? Could there be a flawed mental model? Could there be both? So through many STPA analyses, people have come up with a list of general causes for this type of scenario involving a problem with the controller. Maybe it's easier to think of a software controller here doing something. And this expands on the scenario question that we built earlier. So we found that sometimes we ask this scenario question, you know, why would the SRE decide to not roll back in spite of receiving feedback showing server areas? But the system experts have trouble thinking of specific scenarios. So here's some questions you can ask, given your new understanding of the system through STPA, to help the system experts think of possible causes. So you can ask about responsibilities. Who's making the decision to roll back? Or maybe some end state that the SRE is trying to achieve. You can ask about the decision-making rationale. How does the SRE decide whether to roll back? You can ask about a mental model or the state of the control process. You know, what dashboards or signals are you looking at? How do you interpret them? I heard some people talking about that, to determine production health. And although we didn't show one in our control structure, you could have a higher authority controller ordering the SRE to perform a rollback. So also a case we want to consider. Now, that would actually be an unsafe control action for that higher level controller, and we would analyze that UCA in the course of going through our STPA analysis. Now, very importantly, I'm adding etc. at the end of this list because I want to make it clear this list is not an exhaustive list of questions to ask. However, this is going to give you a good start when you're asking your system experts these questions. Okay, now it's time for audience participation. So the question is, why would the SRE decide to not roll back in spite of receiving feedback showing that there's some correlation between rollouts and server errors? And take a look at these questions that reflect how we model the system. Think about unsafe behavior when we're running STPA. See if you have any new insights to share in Slack. Ooh, there's been a lot of stuff going on while I'm talking here. Great. Okay, the SRE knows it's a false positive. Again, incorrect assumptions. I get human factors, misinterpretation of the feedback. You're not quickly depleting the error budget, okay. The SRE did not realize this particular binary recently had a rollout. I like that one. Low trust in the feedback, all right. Rollout was a critical security patch. You don't want to roll that back, maybe. Ah, yes, people yell at me when I roll back, okay. Yes, that's a good one. I mean, that's all learned decision making, right? Goes into your mental model and your thinking. You might fear that the situation gets even worse. Maybe you get shouted at because it looked bad to the company that you rolled something back. Okay, those are all you're learning this process for making decisions. No run book, culture of fix forward. Oh, these are great. Cache warming up. Permissions, yes, 2 people at the same time. The SRE has no permissions to perform the action. Excellent, I love it, okay. All right, so I think your examples are better than ours, but here's the examples that we came up with. You might have a situation where the dev and the SRE teams share on-call responsibilities. Each of them expects the other one to handle the alerts. Ends up that nobody handles the alert, right? Or I think somebody mentioned similar to this, it could be that a bug was introduced in a rollout that happened some time ago, but the buggy code path doesn't get executed until a new client onboards and you start serving their traffic. So to the on-caller, maybe it looks like the start of errors correlates with the new traffic shape, not with the rollout containing the bug. Or maybe the on-caller considers this particular alert to be oversensitive. I think we had some of those, like they don't trust the feedback. They expect to see these errors, so maybe they decide not to roll back. All right, we've introduced a lot of terminology. We're almost getting to our break here. Now that we've seen a few scenarios, I want to take a minute to really call out the difference between a UCA and a scenario. The UCA, the unsafe control action, is simply the action in the context that makes it unsafe. The scenario goes a step further and it explains what system behavior would lead to that UCA. So the SRE does not roll back to the previous version when the production service is returning errors. And this is because the dev and SRE teams share on-call responsibility and the SRE incorrectly believes that the dev is on duty. So now you're giving an explanation for why that unsafe behavior might occur. Now, notice the phrase incorrectly believes in the scenario. Does that remind you of part of the control structure? Something in the controller? Mental model, yes. So that points to the SRE's mental model, and in this case, the mental model would be incorrect, leading to unsafe behavior. All right, almost to the break. As I mentioned before, so far we've mostly been talking about controller and feedback issues where the feedback is safe. You see that here, feedback coming in is safe. But the controller still does something unsafe. In this case, the SRE does not roll back when production health is impacted. And as with exhaustively exploring the UCAs, or the ways in which an action can be safe, you do the action, you don't do the action, you do it too early or too late, you do it too long or too short. We can also explore the ways in which the behavior in the control loop can be unsafe. And we're really only just getting started with scenarios here. So in addition to cases where the controller does something unsafe, as we mentioned, there's another class of scenarios where the feedback is unsafe. And here's our stick figure illuminating that unsafe feedback. And again, that feedback could be wrong, delayed, incomplete, or missing altogether. Of course, if the feedback is bad, then it's likely that the controller, in this case, the SRE, is going to do something unsafe. So building our question for SMEs is going to be similar to what we did before, only we're going to assume that the feedback is unsafe. And also when we generate the questions to ask our system experts, we're going to specify the true state of the system in question. So this is something that's a little bit different here. We assume the feedback is unsafe, but we give the true state of the actual system, the control process. So for instance, why would feedback not indicate that the service is returning errors, even though it is? Notice that this question is phrased so that the feedback is totally missing is a possible answer. And this class of scenarios has the potential for some really interesting discoveries since, as Ruben mentioned earlier, software developers are very good at designing control paths. Formal design of feedback paths is less common. Now, if you look at some of the published STPA results from all industries and not just software, there are really compelling stories of people drawing control structures for complicated systems, airplanes, autonomous vehicles, factories, manufacturing. And they immediately notice places where there are no feedback arrows. So crucial feedback necessary for a controller to make safe decisions is completely missing. All right, I think it's like 2 slides to the break. Let's come up with some scenarios where the feedback is unsafe. So why would feedback not indicate that the service is returning errors even though it is? And before I read our examples, does anybody have an idea for an unsafe feedback scenario here?
System being monitored is your monitoring system.
The system being monitored is your monitoring system, okay. I like it. JSON blob with an HTTP 200, poor monitoring, monitoring is down, incorrectly configured monitoring, the errors are upstream, synthetic traffic, you haven't reached some threshold. All right, excellent. So here's our examples. You might have no alerts set up for those types of errors. There's a case where feedback is missing completely. Maybe the collection of telemetry is delayed, so that might be a case of rolling back too late. Maybe there are alerts, but they get sent to the wrong group destination. How about an alert storm? And the backend makes signaling out the errors for the production service very difficult. All those scenarios could make the SRE incorrectly believe that the production service in our theoretical incident is healthy or at least doesn't have an issue. And given that belief, the SRE is not going to roll back. Why would they, right? Okay, we've shown you examples of scenario questions for controller and feedback issues. With those questions, you can work with the system experts to anticipate loss scenarios. But again, we've only covered half the control structure. And to make sure we've captured all the possible types of scenarios, we need to analyze control path and control process issues. I'm going to hand it over to Ruben to do that.
So Garrett just talked before the break about controller and feedback issues. Now, but we haven't spoken yet about control path and control process issues. Let's focus on these ones now. As with control and feedback issues, there are 2 scenario classes involving the control path and the control process. In a control path scenario, the controller does the right thing. It rolls back when the production service is returning errors, so there is no UCA. However, something happens along the control path. Someone was mentioning earlier that this can happen. And the control process still gets the UCA. We'll talk about how that might happen in a minute. And finally, in a control process scenario, the controller does the right thing, rolling back the service when it's returning errors, so there is no UCA, and the control process does not get the UCA. However, the control process behaved as if it got the UCA. The production service is not rolled back. So sometimes this can be tricky to reason about, so let's build our scenario questions and think of a few examples. So to build our scenario question, let's first review the UCA we're analyzing. Our UCA is SRE does not roll back to previous version when the production service is returning errors. So the question is, how could it ever be the case that the SRE initiates a rollback, but the rollback doesn't reach production? Now, question for you all. Type your answers in the chat. So before we give a specific example, does anyone have any ideas about a possible control path scenario? Production freeze, failure to find the previous artifact, deployment gates do not allow old version anymore, that's great. Failure to specify the correct version to roll back to, pipeline fails, because we lack a further feedback loop that tells the SRE what versions are in prod. All those great answers. Well, I cannot keep up with the flow. Let's refine the control path scenario question. We have a few examples. There could be more, as you are proposing. So the release system receives the rollback action, but it runs with limited resources. And so it serializes the rollback along other release requests. And it happens that it does not prioritize the emergency rollback. Or the on-caller does not have permissions. This was mentioned multiple times, to rollback. But the release system only reports the permission error in the UI when attempting to start the rollback. And the on-caller doesn't happen to go to the UI and check the status of the rollback. Or an ongoing rollout for the same production service blocks the rollback. There will be more control path scenarios, and that is the goal, to find as many as possible. Finally, we have the control process scenarios, where the controller does not take an unsafe control action, and the control process does not receive an unsafe control action. However, the control process at the bottom acts as if it received the unsafe control action. Remember our UCA? SRE does not roll back to previous version when production service is returning errors. The question here is, why would the rollback reach the production service, but the production service is not rolled back to the previous version? Again, before we give a specific example, does anyone have any idea about a possible control process scenario? Orchestration, control plane borg, upstream change, container stateful set is broken, control process is a zombie. Okay, that's scary. Backlog, yeah, all those great answers. We have a few examples here, so let's refine the control process scenario question. Why would the rollback reach production, but the production service is not rolled back to the previous version? It could happen that the rollback action arrives to the production service, but someone with permission cancels the rollback when they hit a global stop button on the rollout system. Or, this has been discussed in a different form, but the new version of the service was released, which removed a dependency on a backend system. After the release, this now unused, obsolete backend was turned down. When a critical bug in the new version forces us to do the rollback, the process fails because the previous version of the service cannot start now without the backend that had just been turned down. An analogous example is with the database schema migration change. Again, the idea is to find as many of these control process scenarios as possible. And congratulations, we finished all the 4 official steps of STPA, and at this point we sometimes hear people talking about how scary it is to see a list of all the ways or scenarios the system might have an incident. We address these concerns in this last step. If we've done our job right, we have all the information that we need to apply pure engineering, to make decisions on which scenarios require priority fixes, which scenarios can be addressed simply with better detection, and which scenarios we can live with. We accept the risk. Often we find that there are patterns in these scenarios where a single mitigation will have a huge return on investment, preventing an entire class of incidents. And there are many, many ways of prioritizing the mitigations. And this is just an example in which we plot the mitigation across 4 quadrants according to the impact they have on addressing or reducing the severity of the scenarios and the cost of implementing those mitigations. And it can help to show leadership, a graph like this one, for them to make better decisions during planning, for example. And now I am handing it back to Theo for his story time. All right.
Wow, okay, well that was a lot of new material and technical detail about STPA. Thank you both to Ruben and Garrett for giving us a window into that process. So from here on out, you can relax. Okay, take a deep breath. I may ask some questions in this next part of the presentation, but they should be considered rhetorical. You're free to chat and comment in the Slack, but I won't be reading them out loud. So please sit back, relax, and enjoy the show. Now, I'm going to tell you a story about how we applied STPA to the road disruption system in Google Maps. And if you saw the presentation that I gave at SREcon Americas or at the STAMP conference earlier this fall, this is the same system. So here's a friendly reminder of the incident that I presented earlier, where we designed a system that was supposed to ingest and publish live road closures on Google Maps, but it had a key design flaw that we ultimately found with STPA. So let's dive into how this system was designed. If you can recall from earlier, the goal of this system is to process road disruptions from third-party providers onto Google Maps. And so when a road is closed, we should close it on Google Maps. And likewise, when it's opened, it should be opened on Google Maps. Super straightforward responsibility. Synchronize the road closures between those two databases. Now, it would be bad if for some reason this syncing failed and we didn't display a road closure when a provider told us about it. So our users are sad. Now, is this possible? And if so, how come? You're right, it is possible. Okay, well, under the hood, the road disruption system receives snapshots of the closures held by third-party providers. So we see a snapshot here, and that represents the state, of the road closures at a given time. And every 5 minutes, we get a new snapshot. And so what the system does is it diffs the two. So here it figures out that the difference between these two snapshots is this new closure, 25th Street. And so what it then does, it says, okay, well, let me just apply that new road closure onto Google Maps. Wow, that's such a simple system. So now that I've sufficiently explained how the system works, quick raise of hands. How many of you see the glaring issue, or how many, do you think that there is a glaring issue? It's like pretty simple, right? Like you just diff the two snapshots. All right, I count 3 hands, so that's good. Nothing jumps out to me from this specific design, and I'll tell you that this design was reviewed and approved by tech leads of each part of the system. So obviously, the system is safe as a whole, right? Well, did they use STPA to design and review this system? I don't think so. So all of us together, we're going to model this system now using STPA. So as a reminder, there are 4 steps to STPA. 1, define the purpose of the analysis. 2, model the control structure as, with the control and feedback loops. 3, analyze those control structures to identify the unsafe control actions. And then 4, identify the loss scenarios, which essentially is figuring out how those unsafe control actions could possibly occur. And of course, the optional 5th step of redesigning our system to apply our mitigations. Let's dive right into it. So the first step when running an STPA is to define the purpose of the analysis. And so specifically for this analysis, we state the goal. So our goal of this system is to sync the state of Google Maps to that of the third-party road closures. Next, we define the losses. Remember, the losses are the unacceptable outcomes for our stakeholders. So that's going to be the VP of Google Maps, the engineering teams, our users that are driving on and using our product. And so we have 3 losses. 1, loss of user trust. So our users no longer trust that we're going to tell them which roads are closed. 2, loss of mission. And then, of course, 3, a negative PR event. Then we define our hazard states. So the hazard state, as either, I forget if it was Garrett or Ruben who described this, it's a system state or a set of conditions that when together with a set of worst case environmental conditions will lead to one of the losses that we just defined. Now, for the road disruption system, our hazard state is that Google Maps is out of sync with third-party road closures. Now, those of you who are paying close attention might realize that we're almost always in the hazard state in the way that we've designed our system, right? That database is updating all the time, but we sync every 5 minutes. So we're almost always in our hazard state. So that's pretty interesting. Okay, next step. The next step is to build our control structure now that we've defined our purpose of the analysis. So let's model our system. As we can recall, the overarching goal of the road disruption system is to ensure that Google Maps contains the latest state of all third-party closures. So at the very bottom, we have the state of road closures on Google Maps. Now, the controller above Google Maps is the road disruption processor, who is responsible for synchronizing that state. And it does so by sending create actions or delete actions, right? You see right there, and it receives feedback from Google Maps, specifically the road closures of it. However, how does the processor know how to change the state of Google Maps? Well, let's add another controller. And this controller owns the responsibility for telling that processor which closures to open or close. And finally, we have the engineering team. So what's really interesting about STPA is that it doesn't just model the technical parts of the system, but also the human parts. Okay, so it allows you to model the humans that interact with your technical systems. So this engineering team, they own the logic of the snapshot differ, and they also own the logic of the processor. And they're also the ones who should be paged when Google Maps is out of sync. All right. Step 3, unsafe control actions. Let's look at this one in particular. Now, it would be unsafe for the snapshot differ to not create a road closure when that road closure exists in a new snapshot, but it doesn't exist in Google Maps. In other words, when there's a new road closure, it should be applied onto Google Maps, and so it should provide that create action. And it would be unsafe for it to not do that. And if this particular UCA does not happen, rather if it does happen, then Google Maps will be out of sync with the snapshot. So how can this actually happen? Well, let's start looking at the feedback. So what feedback does this controller receive here? Well, it receives third-party snapshots, but hold on. The UCA refers to the state of Google Maps. And the state of Google Maps is not at all provided as feedback to the differ. So how on earth does the differ know when Google Maps is out of sync with a snapshot? Now, as we can recall earlier when I was describing the underlying system, the differ's mental model assumes that the previous snapshot is equivalent to the state of Google Maps. But is that assumption always true? What happens if the previous snapshot does not equal the state of Google Maps? Can that happen? Well, let's dive in deeper. Okay, so we're trying to figure out whether or not its mental model can be wrong. The mental model of, essentially the prior snapshot always representing the state of Google Maps. So the snapshot differ. What does it do? Okay, it generates road closures by comparing the two previous snapshots, and in this case, it sends a create for a 25th Street closed. But what if our command to create that road closure doesn't work for some reason? Perhaps the database update failed, or we never sent the create message, or there was some race condition between the snapshots, or some problem exists in the road disruption system or Google Maps, and any of those could result in 25th Street closure not being applied onto Google Maps. Now we're in the hazard state. So what happens next? Can the system actually recover from this incident? Well, let's add a third snapshot to see what happens. So in the third snapshot, the road disruption compares snapshot 3 against snapshot 2, and it sees no diff for 25th Street closed. And what that means is that it'll never reattempt to publish that closure. Aha, so now we can see how this assumption can be incorrect. Well, what happens? Our system will happily chug along and update other closures without ever retrying that 25th Street closure. And the end result is that we're now completely out of sync with the state of the world. Days or weeks later, the missing road closure on 25th Street is what results in all of our users being upset and me getting paged. Now we're in a lost state. You see, the road closure could have gone missing days or weeks prior to users navigating on this road. The key problem here is that the road disruption system had the wrong belief about which closures were on Google Maps. All right, rhetorical questions, though you can answer on Slack if you're feeling compelled. Which component reliability tools would you use to fix this? Add redundancy? Improve component quality? Would you add better testing? Finer grain monitoring? Would you limit damage with failure isolation? You see, it's unclear to me whether any of those component reliability strategies would actually work well to account for this design flaw. In this outage, no component necessarily failed. You see, every component operated as designed. The key problem here is that the system had a design flaw. Okay, so let's take a quick recap of what I shared with you. This design has a serious flaw that resulted in missing road closures. And this results in our loss scenario. You see, our missing road closure results in users being routed across a parade, which causes negative PR. And then of course we spend 20 weeks trying to figure out what happened, then redesigning our system, and then relaunching it, okay? 20 weeks, all right? However, here's what actually happened. What actually happened is that we discovered this design flaw by using STPA. Sorry, I missed a slide. Okay, so this is our new design, of course, which is to just read from the database. You might have been crying from the peanut gallery. Of course, just read from the DB. Well, we actually discovered this design flaw using STPA. And as I stated earlier, this incident never actually happened because we used STPA to analyze the system before we built it. So this problem was actually fixed by rearranging or rewriting paragraphs in our design doc. So our new design reads from the database instead of comparing against the previous snapshot. And when we illustrate that in our control structure, this new design essentially just adds feedback from Google Maps to the snapshot differ. You might say, great, okay, wow, you found this one thing. So what? Well, not only did we find this specific design flaw, we actually found 6 other design flaws too, including invalid ordering of operations, feed processing race conditions, insufficient feedback about sync state, error-prone onboarding, inadequate change management support, and limited observability into the processing of road disruptions. Whew, I'm a little winded. That was a pretty long list of design gaps for a design that had been approved by tech leads. So you might be asking yourself, how is it possible that these design flaws were missed using our traditional review methods? Well, let's think about it. Oftentimes, we build software and we design it that's in a way that's focusing specifically around the happy path, right? And by definition, on that happy path, you assume that the state of the system is always safe. And when we do think about the unhappy path, we don't have the tools to methodically interrogate the safety of our system. And the intuitive methods that we use at the beginning of this talk are actually super time-consuming, and they're not methodical, right? Because we rely on some random walk of this entire system state space, which in systems like these are often way too large to even pretend to do properly. Someone in the Slack earlier was talking about computational complexity and then like the combinatorial explosions. This is why our intuitive methods are very time-consuming and ultimately ineffective. And as a result, we choose mostly to ignore it. Now, the benefit of STPA is that we can abstract away a lot of that complexity using these hierarchical control and feedback loops. So, without STPA, we would have spent 5 weeks or months to fix these failure modes because we would have found them in the testing or production stage, so big O of months. With STPA, we shifted the identification of those failure modes to the design stage, which vastly reduced the cost to fix them. Now, for this specific system that I showed you, the road disruption system, the cost of identifying and fixing those 7 design flaws was incredibly cheap. It cost us 26 engineering hours total to run STPA. And the per fix cost was under 4 hours per flaw, which otherwise would have taken us months or weeks per flaw. Now, that's not a 10x engineer. That's a 1000x engineer, so I put that on my perf. Hi, I'm a 1000x engineer. Now, the cost of fixing this problem increases exponentially, right, as your product becomes more mature. So engaging with your SWE teams early when they're designing a new service or system is most effective. Now, it's not like we were doing it wrong before. We really just didn't have the tools to identify this whole other class of outages. Now, when we applied STPA to mature systems at Google, we still find tons of safety gaps. But we face more significant resistance from the engineering organization because we effectively ask our engineers to unlaunch the system and then rebuild it from scratch, all for a bunch of quote-unquote hypothetical safety issues. However, when we applied STPA to the designs of our systems, our product engineering partners are way more interested in engaging with us because we're coming to them with fixes for the design, and we're working together to improve their designs, right? So this helps them have fewer outages in the future. And as a result now, we're getting a huge inbound of requests for new analyses from our partner teams. Great. So what did we learn? Well, when we apply STPA to designs, before we implement our systems, we have the opportunity to fix our problems at a fraction of the cost. STPA enables us to methodically explore the entire space of unsafe system behavior. Now, you too can learn how to do STPA on your systems with some help, of course. Now, what help, you might be asking? Well, here are some great resources for you to look at. Unfortunately, these are actually not URLs. These are blue links. I realize that right now. When the slides come out, please click those links. Google has some STPA resources. The folks at MIT also have some great resources, and there are also several conferences that they host per year, one virtual in September and one in person in March. Those are free conferences, so I would highly recommend you check it out. Okay, and with that, thank you so much, and we're super happy to take some questions with the remaining time that we have.